the EM field of the chip. And, oh, it's moving. And in the top there's an oscilloscope. And again, there's a wide range of devices you can use. I think that thing is about 15,000 euros. But on the desk here, I've got one that's 1,500 euros. So, and it still, applies. So also that is something, again, for the cost of attack to factor in. So the question is how can you set up something like this and attack a device? What kind of other activities do you need? And when you do sidechain analysis, and you may have seen that yesterday, you need a few prerequisites. Of course, you need access to the side channel. If it's a power measurement or an electromagnetic measurement, or you need to measure the timing of something and you need a trigger line somewhere to measure it from. So you need to have that access. If you don't have it, then the whole attack doesn't work. If you're doing a so-called differential attack, a crypto attack, you do need to have input or output data of the crypto to be able to do your attack with. So you take your measurements, but you still need to get that data. If it's all embedded into a system and a protocol that's difficult to penetrate, then already that represents an effort to overcome. Then you need to minimize the noise. And again, for smart cards, there's been devices designed to minimize that very much. However, in an embedded system, you're dealing with the power supply that's being given to you by the embedded device. And, well, we'll see what you can do or have to do to overcome that. You need to know what to measure. If you know that a hardware crypto operation maybe takes a microsecond, and you have an embedded device and it goes in over Ethernet or a serial cable, when does it happen, that single microsecond that you want to measure? So you need a trigger signal. And can you derive it from the design, or do you need to implement something yourself to be able to do that? And then you need to link the data to the operation that you measured. So you need to know this measurement was this data going in. And if you've got a stream of data going in and you have crypto going on, it may be quite difficult to match up the measurements and the crypto and the data, and your whole attack won't work if that doesn't match up. It's a statistical attack, so it's very sensitive to that. So you see there's a lot of prerequisites that you need to take into account before you do an attack. And then we switch back to smart cards. The reason being, like I said, 10 years of testing on smart cards sets a benchmark, a body of knowledge of how you do this on these cards and how you set them up. And of course, it's difficult to convey all that knowledge now and directly into the room, but I'll use a few tables to compare some of these things to an embedded system to explain a little bit of the difficulties. The tables are quite big, so they'll be posted on the web. I won't go over every entry, but it's kind of a brain dump of things that we come across. If you look at a smart card, you see the contact pads. It's all been ISO standardized. So that makes the testing also much more convenient, because you know what the power line is, you know what the input line is. You can send data in and trigger and do your whole acquisition process fully automated because of this kind of standardized interface. And that's one of the big changes when you go to an embedded system. So if you think about a smart card processor, in general, we talk about a microcontroller. It's a CPU. They're getting bigger, but still, for instance, the crypto core is still like 20% of the die, and it's still a tiny engine compared to all the CPUs we use around ourselves today. So if you start comparing to a smart card what a maybe more complex embedded system would look like, you already see that there's a lot of things to take into account. For instance, a lot of the complex CPUs these days have multiple processors inside. So how do you know which one is doing your stuff, and how do you isolate that one from all the others doing other stuff, which is all noise, compared to the smart card that's just doing what you tell it to do, namely generating a certificate or something like that. The engine itself, the crypto engine, on a complex CPU is just a building block, and they can scatter 10 or 20 AES cores over the chip, whereas the smart card has only one, and it's D1. So you get more like the needle in a haystack kind of feeling when you look at a complex CPU compared to a standard smart card. However, there are also other parts, and that is, for instance, that a lot of crypto in embedded systems is in software, or partly supported by software. Also, there are no countermeasures. We hardly encounter any countermeasures in embedded systems compared to smart cards. So there are pros and cons if you look at this picture, but if you have a high-end CPU, I think the cons outweigh a little bit the pros. If you look at acquisition, so like I said, if you have a standardized ISO interface, you can do your measurements and measure your power. What about an embedded system? Well, everyone now knows the PCBs, and you have seen the sites, and maybe you built them yourself. How do you measure the power line if it is a multi-layer PCB and the components are very close? So you get the challenge of just getting access to the channel is already part of the attack, which weighs in, whereas the smart card you just insert in your reader and you're done. However, there are also advantages. A smart card interface is relatively slow. You cannot change the behavior of the interface. Whereas the embedded system, it may be modular, and you may be able to replace some parts without endangering the crypto part, but it may help your attack. So you can customize the embedded system more for your attack than in the case of a smart card, where you just have to deal with what's given to you. Also the power. We see embedded systems taking, in the set-top box world, taking a few amps. And in the gaming, it's even worse. It's like 1/10 of amps. How do you measure that compared to the milliamp voltages of a smart card? So again, it's not a black and white picture. You see things that are much more difficult, and there are things that are actually much more attractive. One of the attractive things in embedded system is if you can customize it, it often can run much, much faster than a smart card. And for a DPA attack, you need measurements, and to encounter or overcome noise, you need a lot of measurements. So now I can do, we have done on some chips 5 million measurements or more in a day, whereas for a smart card that's maybe a week or more. So you have some things that actually work in your advantage. So when you start thinking about testing, what do you encounter? First, a small remark about testing and attacking. We are a security testing company, and that means that we don't have to go through the full attack like a real attacker would have to go. That means that if you have an embedded system and half the time that's spent on reverse engineering how it works, we generally don't have to do that. We can focus on an engine that we want to know the leakage of and concentrate all our work on that. If we then have a finding, then we can just translate this to the world outside and factor in how much time people would have to spend to reach that stage to see if it is a problem for the product, yes or no. So most of our work is focused at creating the optimal testing environment as opposed to having the most realistic attack. But still, that means that we have to overcome and understand, of course, a lot of these aspects that everyone has to overcome. What do you need to do? Well, first of all, you need to control the crypto. Like I said, you need access to the data. You need to be able to trigger on it. So you need to be able to know when it happens, and preferably actually cause the crypto to operate. In the ideal world, I pass the data in, and it happens, and then I measure at the right time. So reaching that stage already needs preparation. Then I need, of course, to link the data with the measurements. I need to okay. I thought the tent was collapsing, but it's not so bad. The efficiency of the acquisition is something you may want to look at to optimize that, to improve your attack. And like I said, you need to balance the increased efficiency and the increased complexity. A few examples. So timing analysis.